This lecture covers the special detailing provisions for earthquake structures, mainly for reinforced concrete structures, in accordance with the National Structural Code of the Philippines, NSCP 2015, or the ACI 318-14. The question is, why is there a need for special detailing provisions? Aren't the sections 401 to 417, including 419 to 426, aren't enough to keep our buildings earthquake resistant? Note that in Chapter 2 of the Code, the detailing requirements in Seismic Zone 4 must meet the requirements in Section 421 of the Code. Now, the answer to this question partly lies in understanding the difference between these two: being strong and being tough. Being strong in the sense that our structural elements can support or withstand extremely large loads. But if this is subjected to a cyclic loading, they may be subjected to a brittle failure. They may exhibit signs of distress, even failure when they are subjected to lesser loads but which are applied quickly and repeatedly. On the other hand, being tough, they can also support or withstand large loads. They are also capable of withstanding frequent or repetitive applications of loads, or what we call the cyclic loading, and they are also capable of energy dissipation. Being tough may also exhibit the property of being ductile, meaning to say it can undergo large deformation without loss in their ability to support the superimposed loads. Or the ductility is the ability of the structural system to undergo large deformations without collapse. All in all, we need our structures or structural elements to be strong and to be tough. Let's now jump to the provisions of earthquake resistant structures. You may find this one at section 418 of the NSCP or in chapter 18 of the ACI 318-14. In the Philippines, we have two seismic zones, the Seismic Zone 2 and Seismic Zone 4. Seismic Zone 2 covers Sulu, Palawan, and then Tawi-Tawi, and the rest of the countries are in Seismic Zone 4. In Seismic Zone 4, the minimum lateral force resisting system shall be of special moment resisting frames, meaning to say your frames will be subjected to 100% gravity and then 100% earthquake loads. Moreover, when your structural elements has been subjected to seismic and wind analysis, and such that the wind analysis governs, still the detailing requirements and limitations of your sections shall be based on section 208 of the code. Beams of special moment resisting frame. Let's go with its dimensional limits. So this applies to beams of special moment resisting frames. The clear span shall be at least 4 times the effective depth. Width to depth ratio shall be at least 0.3. The minimum width or the breadth of your beam shall be 250. And it can happen that the beam is wider than the column, provided the projection of the beam width beyond the width of the supporting column on each side shall not exceed the lesser of C2 and 0.75 of C1. C1 being the longer column dimension. So to illustrate that one, you have here the length of the SMRF beam should be greater than or equivalent to 4 times the effective depth. Okay, so this is the effective depth. That would be the height. So you add up the half of the centroid of the bar, the stirrups, and then the concrete cover, you have the height. The breadth minimum of your beam is 250, and to get the ratio of the breadth and the height, that should be greater than or equivalent to 0.3. And if you have here a column, C1 being the longer dimension, and then this is C2, it can happen that the beam is wider than the column. So the projection here is the smaller of the two. It can be C2 or 0.75 of C1. So your beam width is equivalent to C2 plus 2C2 or plus 2 times 0.75 of C1. Well, the definition of 4 times the effective depth, this is a short beam already. For the flexural reinforcement of a SMRF beam, there should be 2 bars on the top, and then there should be 2 bars at the bottom. So all in all, the minimum are 4 bars on corners. And we need to comply for the AS greater than the minimum. So either greater of these two again, the square root of FC prime divided by 4Fy, or 1.4 divided by Fy being the steel ratio. And then to avoid congestion on the beam, the maximum reinforcement should be 2.5% being on the steel ratio. So 0.025 times the breadth times the effective depth. Moreover, for a positive moment strength at the joint face shall be at least 1/2 of the negative moment strength. So this is at the support provided at the face of the joint. Both the negative and the positive moment strength at any section along the member length shall be at least 1/4 the maximum moment strength provided at the face of either joint. And note, AS minimum need not to be satisfied if AS supplied is 1/3 greater than the AS required. Okay, so to illustrate that one, I have here a typical example of a beam. So you have the column, you have the beam. This is the point of inflection. So under the tension bar, okay, so the steel area here should be greater than the required from your analysis. Okay, it may be equal or greater than from your analysis, and then greater than or equivalent of the 2 bars. Okay, so 2 bars minimum at the top, 2 bars minimum at the bottom, and this should be greater than or equivalent to the minimum AS required, and then should be less than the maximum to avoid congestion on this part of your beam. And then at the bottom, okay, for the compression bars, this should be again greater than or equivalent to required from your analysis, or greater than for as 2 bars, greater than your minimum area. And then for earthquake provision, so this should be divided by 2. So whatever the area of the number of bars here, that would be divided by 2. From the points of inflection, there is now the development length to be extended from these bars. In terms of the number of bars, so if this is 6, you divided 1 by 3. So there are 2 required bars to be extended beyond these points of inflection. So at what length, you try to calculate these criteria: greater than or equivalent to the effective depth, greater than by 12 times the bar diameter, or L divided by 16, the clear span divided by 16. And beyond this development length, there should be the number of bars to be extended continuously, and that is AS max divided by 4, or you can refer to this equivalent to number of 2 bars at the top and then bottom. For the lap splicing, the splices are not allowed within the joints of the beam and column, and no splices are also allowed within 2H, or twice the height of the beam from the face of the joint. No splices are allowed within 2H from points of flexural yielding as a result of lateral displacement. And lap length must be provided with hoops. So this is seismic hoops or spiral with a spacing of d over 4, the effective depth divided by 4, or 100. So on the part of the splicing, splicing is not allowed within this joint if this is a continuous beam, and within the twice of the height of the beam, no, the splicing is not allowed here. So beyond this point, you can splice. Again, for twice the h, you are not allowed to splice within this area. For the transverse reinforcement of the beam, the design shear force VE shall be calculated based on this assumption. So V is different from your VU. VU is coming from your analysis. No? The VE is from forces on the beam between faces of the joints. So it's acting on this manner. It's acting on that manner. Assume that the probable flexural strength acts in opposite direction. Assume that the beam is loaded with factored gravity loads, just the same. So V is calculated on this manner. You have the probable moment at the left, or it can be designated as 1, plus the probable moment at the right divided by the clear length plus minus the VU. So, but the probable moment must be calculated for a flexural tensile reinforcement of 1.25 Fy. For the transverse reinforcement over the confined region, which is the 2H, shall be proportional to resist shear, assuming Vc is equivalent to 0 when both of the following conditions occur. So if this happens, that 1/2 VE is less than the probable moment at left plus the probable moment at right divided by the clear length, and the axial load acting on that beam is less than 0.05 Fc prime of area gross. No? If this is not the case, then we need to calculate the capacity of your concrete, which is equivalent to 1/6 square root of Fc prime B times the effective depth. In beams of having factored axial compressive force exceeding Pu greater than 1/10 of area gross of Fc prime, hoops shall comply with the columns requirements provided within 2H from the face of the support. Along the remaining length, hoops satisfying the column requirement shall have a spacing not exceeding the lesser of 6 times the bar diameter, or 150. So this is the magic number in earthquake, either 6 times bar diameter or 150 as maximum spacing. The spacing of hoops shall be d/4, or 6 times the diameter of the main bar, or 150. Again, 6 times bar diameter or 150 within the 2H. And I have here a notes, no? Corners and alternate longitudinal bars shall be provided with a lateral supported by a tie with included angle not more than 135 degree and no farther 150 mm from such laterally supported bars. At the same time, where hoops are not required, stirrups with seismic hoop at both ends shall be placed at a distance not more than d/2 as a spacing throughout the length of the member. Of course, this will terminate until the midspan of the beam. So to illustrate what I'm saying, I have here a beam. Okay, so again, from the face of the support on earthquake resistance structure, it's automatic that would be 1 at 50 spacing, no? And then until the 2H, okay, so until the 2H 1 at 50, and then until the 2H you have this spacing, either d/4 less than or equivalent to d/4, 6 times the bar diameter, or 150 as the magic number. And then beyond 2H, okay, you can have a spacing of d/2. And then if you have a lap splices, you go back again to that spacing I have discussed a while ago. And for a seismic hook, no, this is a 135 degree, and then the extension part here should be 6 times bar diameter, or maximum of 75 mm, or 3 inches. And then the spacing of the cross ties that is being laterally supported should be 150 maximum. So for standard hooks and for development of the deformed bars, you can refer to table 25.3.1 and then 25.3.2 For a 90-degree hook, you have your extension length here. So the extension length is 12 times bar diameter, acting on the 90-degree manner. And then for 180, that is 4 times the bar diameter and 65. For development lengths and hooks, you may refer to this section of 9.7.3.8.1. Okay, the length of development length can be calculated on this formula. Okay, so you have your modification factor based on the type of concrete, either lightweight or normal weight of concrete, the epoxy, and then the size, and then the casting position. And then for the form bars in tension terminating in a standard hook, you may refer to your development length on this criteria from A to C. So this formula, and then times 8 times bar diameter, or 150. Now let's go with the column of special moment resisting frame. We have our dimensional limits again, that is to be applied for columns of special moment resisting frame. The least cross-sectional dimension should be greater than or equivalent to 300 mm. And then the ratio of the least column dimension to bigger column dimension should be greater than or equivalent to 0.4. Okay, so this one. So you have the B greater than or equivalent to 300. And the ratio should be greater than or equivalent to 0.4. Of course, the capacity of this column can be plotted through an interaction diagram of the moment to the action load. On the longitudinal reinforcement of your column, the minimum reinforcement shall be 1% to 6%. And then 4 pieces of rectangular column. So 4 bars on a rectangular column, 6 bars on a circular column. And then the clear spacing of longitudinal reinforcement shall be 40, or 1.5 times bar diameter, but not more than 150 as the maximum. Lapse prices shall be permitted only within the center half of the member length of the column. So usually the midspan shall be designed as tension lapse splices, shall be enclosed with a transverse reinforcement equal to this spacing. So 1/4 of the minimum column dimension, 6 times the bar diameter of the smallest longitudinal bar, and then S is equivalent to 100 plus 350 minus HX all over 300, wherein the range of this S on the third criteria should be greater than 100 but maximum of 150. Again, we're going back to 6 times bar diameter or 150 as the magic numbers for our spacing. In addition, the lapse splicing length shall be at least of 300 mm. And 50% of the bars at any section except for the confined zone of the column are allowed to be splices in a staggered direction. Closed hoops or continuous spirals must be provided for the following function. Of course, to confine the concrete core, to act as a lateral support of the longitudinal bars, and then to resist shear. The amount of transverse reinforcement must be larger of that required for confinement or the design shear, specifically for those part of a soft story column. The confined zone of the column can be calculated on this manner: greater than of the highest among these three, the bigger column dimension, the clear length divided by 6, or greater than or equivalent to 450 mm. And the spacing of the transverse reinforcement can be calculated based on these following conditions. If PU is less than or equivalent to 0.3 of area gross FC prime, or your FC prime is less than 70 megapascal, then you need to calculate A and B alone. So whichever is greater of A and B, then you equate this one to the area of your required shear reinforcement divided by the spacing times BC. So depending on the side you're considering, either on this longitudinal part or on that transverse part. Well, this labeling is incorrect for the part of BC2 and then BC1. BC1 should be measured from the ties to tie. At the same time, BC2 should be measured from the ties to ties. You have your notations here. For the design shear force, VE for column need not exceed those calculated from joint strength based on MPR, the probable moment of the beams framing into that joint. So why is this so? Because we allow the beam to fail first rather than the column. And then MPR, of course, this is now the capacity of your column based on the range of factored axial loads acting on that column. In the analysis, we need to calculate the probable moments at top and bottom of the column to calculate for the design shear of the column. Again, the design shear of the column is equivalent to the probable moment at top plus bottom divided by the clear length of your column. On the analysis of the joint, we now have a free body diagram which looks like this. So this is based on the tension bars on the left side, tension bars on the right side for the beam. Then you have the capacity of the concrete, and then you have the design base shear of your column, and then the probable moment of your beams from left to right. And then we can cut now this section, and then we can separate either top and bottom for us to get the shear joint capacity of your connection, the beam column connection. The transverse reinforcement of the columns over the length of LO shall be designed to resist shear, assuming VC is equivalent to 0 when both of the following can occur. If not, then we need to calculate again VC based on this formula, 1/6 times lambda square root of FC prime BWD. You have the detailed method for calculating VC on this table 22.5.5.1. Okay, so again, the confined reinforcement for confined zone of the column is located at the length of LO. So greater column dimension greater than the clear length divided by 6, and then greater than or equivalent to 450. And then you are not allowed to splice on the joint again. You are not allowed to splice on this zone. Beyond that one, you are allowed to splice. And then the spacing until LO should be less than or equivalent to H1/2 over 4, least column dimension divided by 4, and then or equivalent to 100. And then beyond LO, you can have the magic number again, 6 times bar diameter, or 150 mm. For a rectangular ties, you have a minimum of 4 bars, and then for a spiral, 6. And then the spacing, the pitch, of course, the concrete should fill the gaps here. So the spacing should be greater than or equivalent of 25 mm, but a maximum of 75 mm or 3 inches, or greater than times 1.33 times the maximum aggregate size. For the strong column weak beam criteria, so after you have established the probable moment at the beams and columns, then you can just come up with the summation of moment of column divided by the summation of moment of beam. That should be greater than or equivalent to 6/5 or 1.2. Again, for forces in longitudinal beam reinforcement at the joint face shall be determined by assuming that the stress in the flexural tensile reinforcement is 1.25 of Fy. So this T1 here will be calculated as ASFy, but that Fy will be substituted to be 1.25 of Fy. That 1.25 is the expected yield strength of that bar, meaning to say grade 40 is not grade 40, no? So it can go beyond grade 40. For the shear joint capacity, of course, we go back to this analysis again, that we try to cut off the center half of this one and then separate the upper free body diagram for us to determine the joint shear capacity of your beam column connection. Now what we need to do here is to get the effective joint area of our beam column connection, and there are provisions again to follow, no? The effective joint width shall be equivalent to B plus H. H is the joint depth, or less than or equivalent to B plus 2X, no? So basing it on this configuration. So the joint width shall not exceed the lesser of A and B. So after we get the V joint here, we need to compare that one BC. Depending on the joint configuration, if that is on all 4 faces, 3 faces, and other cases. So either equation 1 or 2 for 4 faces and then 3 faces. 3 faces being in the corner. So this would be the analysis for you to check the shear joint capacity. In summary, for earthquake resistant structures under reinforced concrete having the special moment resisting frames as our structural system, we need to check the 4 items: the dimensional limits for SMRF beam, dimensional limits for SMRF column, the strong column weak beam criteria, and then the shear joint capacity. For further references, you may refer to these authors of the textbook. You have Arthur Nilsson and then Jack McCormack.